So the first question, we're dealing with lone electrons. Were different elements. Now lone electrons, if you draw the orbital diagram, are electrons that just only one electron occupies an m sub L value. That's called a lone electron. So you have lone electrons, you have paired electrons. Of course, paired electrons, when two electrons are together, one is pointing up, which is denoted as plus a half spin of an electron, and one is pointing down, denoted as minus a half spin of electron. It's common practice to always put the first one pointing up and the second one pointing down. So now we'll take a look at each one of these and determine how many lone electrons are in each. So we have antimony, and the best way to do this is first by starting off writing the electron configuration of antimony. So it's going to be argon 4s2 3d10 4p3. Now, as far as 4s2 3d10, these are completely filled orbitals, so you can imagine there's not going to be any lone electrons in those. Those are all paired up. Now with the 4p, you see we only have 3 electrons, and if you remember from previous lectures, the p orbital has 3 degenerate orbitals. So 3 m sub L values. So this is what the 4p looks like. And so according to Hund's rule, each degenerate orbital needs 1 electron before you start to pair them up. It's the same thing like on a bus. Every person wants to sit in their own seat, and you only start pairing up passengers once all the seats are filled. And so this would have 3 lone electrons. Next we go to osmium. Osmium is located here on the 6th row. It's a transition metal. So again, we're going to start by writing the electron configuration of osmium. Is going to be xenon 6s2 4f14 and 5d6. Now again, you see that the 6s orbital and 4f orbital are completely filled, so we know that there's not going to be any lone electrons from those 2 orbitals. Now if we investigate 5d a little further, because you see it's partially filled, we'll see how many lone electrons we have, if any. So again, it's 5d6. So the d orbital has 5 degenerate orbitals, so 5 dashes. They should be all level, but I can't draw in a straight line for some reason. And so now, according to Hund's rule, again, this is the 5d orbital. According to Hund's rule, each degenerate orbital gets 1 electron before we pair it up. So once everyone gets 1, then we go back and we start to pair the electrons. Now here we see that osmium has 4 lone electrons. So Hund's rule is very important. And I didn't notice this when I wrote the question, but now we have ruthenium. And if you notice, ruthenium is right above osmium. So you see ruthenium, osmium, they're right above one another. And so ruthenium would also have 4 lone electrons because it's going to have a similar electron configuration as osmium. So it'd be krypton 5s2 4d6. So it would also have 4 lone electrons. Now we get to molybdenum. So molybdenum, we write the electron configuration. It's krypton. Now wait for it. Molybdenum is an exception, so you have to remember how to write the electron configuration for this exception. So it's going to be 5s1 4d5. And so here you see we have a half-filled s orbital and a half-filled d orbital. Since they're only half-filled, you know that all of these are lone electrons. So this would have 6 lone electrons. And it's very important that you remember the exceptions for electron configuration. Again, the 2 exceptions are chromium, molybdenum, copper, silver, and gold. That's the only 2 you need to know. Now we're switching gears. We're talking about lone electrons in each ion. And the reason I like to use lone electrons is because it's a way for people to be able to do the orbital diagram to determine or write the electron configuration to determine the lone electrons rather than just having to write the electron configuration for every question. So before we get into each one of these, just a few rules about electron configuration of ions. So for S block cations, you only remove from the last s orbital. These are things like sodium plus, calcium 2 plus. These are s block cations. You only remove electrons from the last s orbital. So you always remove electrons starting with the highest energy orbital. With that said, when we go to p block cations, remove from the highest p orbital, remove electrons, I should say, from highest p orbital then the highest s orbital. Okay, that's p block cations like aluminum plus, tellurium plus 4, etc. Never from d orbital. So for p block cations, it's always going to be the highest s and p. That's it. Never from the d orbital. For p block anions, add electrons to the last p orbital. And then the main one is the d block cations. And here you remove electrons from the highest s orbital first, then the highest d orbital. So that's kind of a summary of how the different ions behave. And so the reason the d block, it's the highest s and then d, is because, I know this is going to sound circular, but before you add electrons, for example, the 4s is lower than the 3d. That's why we added to the 4s and then the 3d. Once you add electrons in it, then it flips, and the s orbital, the 4s, becomes higher in energy than the 3d. So that's why when we're doing transition metal cations, we take from the s first and then the d, because once you add electrons, it switches on. And so with that said, now we can look at these ions. So again, copper plus, first I like to write the electron configuration of copper. So that's going to be argon. Now remember, copper is an exception, so it's going to be 4s1 3d10. Because remember, it's a half-filled s orbital and a full-filled d orbital. So now when we want to make, and let me specify this as copper here so no one gets. So if we want to make copper plus, well, that means we're going to remove from the s orbital first. So we're going to get rid of this one electron in the 4s. So then copper plus is argon 3d10. And since copper plus is a completely filled d orbital, it has 0 lone electrons. So that's copper plus. Next we move to arsenic 3 plus. So we write the electron configuration of arsenic. So again, this is a p block cation, so we're going to remove from the highest p orbital first. So we remove 3 electrons from the 4p orbital. So when we write the electron configuration of arsenic 3 plus, we get this. So notice that these are both completely filled s and d orbitals, so this has 0 lone electrons. Next we get to niobium, and niobium is located on the 5th row. If we write the electron configuration of niobium, we get krypton 5s2 4d3. Now again, with transition metals, we have to remove from the highest energy orbital first, which will be the 5s in this case. So since it's niobium 2 plus, we remove the 2 electrons from the 5s orbital and we get this electron configuration. Now remember, with a d orbital, you have 5 degenerate orbitals, and so if you have 5 or less d electrons, then those are all going to be lone electrons. So niobium 2 plus has 3 lone electrons. Lastly, we have cobalt 2 plus. So let's first write the electron configuration of cobalt. So cobalt 2 plus, what that means is we remove from the s orbital first. So these 2 electrons go away. And we have argon 3d7. And so if we were to draw the orbital diagram of the 3d orbital, it would look something like this. So now again, Hund's rule, every orbital, degenerate orbital, gets 1 electron. So that's 5, 6, 7. So cobalt 2 plus has 3 lone electrons. So now we're getting into the magnetic properties of elements and ions, and there's 2 ways we can describe an element or ion. We can describe it as paramagnetic or diamagnetic. And so paramagnetic means it's attracted to a magnetic field, diamagnetic is not. And so the way we know something is paramagnetic is it has lone electrons. So if it has lone electrons, it's paramagnetic. Diamagnetic means it has no lone electrons. Now for elements, and pay attention here, this is important, for elements, there's only a few groups on the periodic table that are diamagnetic, meaning no lone electrons. So the groups that I'm going to highlight on the periodic table are the ones that are diamagnetic elements. That means they have no lone electrons. The rest of the elements will be paramagnetic. So if you can just remember the groups that are diamagnetic, and there's not many, less than your 5 fingers, then everything else is paramagnetic. So the first group is group 2. Alkaline earth metals are diamagnetic. They have no lone electrons. They have a completely filled s orbital. The next group is the one involving zinc, cadmium, mercury, and whatever's below mercury. These all have a completely filled d orbital. So these are also always diamagnetic. And then lastly, the noble gases are always diamagnetic when they're in their element form. So again, this is only when we're talking about elements, not ions yet. So group 2, the group with zinc and the noble gases, these are the only groups on the periodic table that are diamagnetic elements. Everything else is going to be paramagnetic. So when we look at iron, iron is not in one of these three groups, so it's going to be paramagnetic. Calcium, calcium is in group 2, so it's going to be diamagnetic. Tin is not in one of these three groups, it's in group 14. This would be paramagnetic. Cadmium is in the group with zinc, so this would be diamagnetic. And then lastly, zirconium is located here. It's not zinc, cadmium, or mercury, and it's a transition metal, so it's going to be paramagnetic. And so that's a quick way to determine if an element is para or diamagnetic, is by knowing that only these three groups highlighted in the different colors are diamagnetic. And lastly, we want to look at ions and determine if ions are para or diamagnetic. And I can give you a few tips here that will help. But there's lots of different tips. So for example, main group, or I should say group 1, and these are not all of them, these are just some things you can remember to help. Group 1, group 2, and group 13, so that's with aluminum's group, cations are diamagnetic. So that's one thing you can remember. What else? Anions are generally diamagnetic. So like O2 minus, S2 minus, P3 minus, Br minus. So all of the anions generally are going to be diamagnetic because they have all paired electrons. Now the only other tip I can give is that, for example, zinc 2+, cadmium 2+, mercury 2+, these are also diamagnetic. Other than that, it's best if you investigate the elements. But these are some general tips that can kind of make the process a little smoother. So with that in mind, we'll take a look at each one of these. So first we have palladium 4+. So we write the electron configuration of palladium. Be krypton, 5s2, 4d8. Now, it's palladium 4+. What does that mean? That means we take 2 electrons from the s orbital and we take 2 electrons from the d orbital. So we get the electron configuration for palladium 4+. Be krypton 4d6. Now you don't have to draw the orbital diagrams for this. As long as you have less than 10 d electrons it's always going to be paramagnetic. So this is going to be a paramagnetic ion. Next we have silver. So we write the electron configuration of silver. It is krypton. Now remember, silver is an exception. So it's krypton 5s1 4d10. So to get us silver plus, we remove one electron from the s orbital. And so then silver plus would be krypton, krypton 4d10. So since you have a completely filled d orbital, it's not going to have any lone electrons, so this would be diamagnetic. Next we have chromium 4 plus. So let's first write the electron configuration of chromium. It's going to be argon. Now remember, chromium is an exception. So it's going to be argon 4s1 3d5. So to make the ion, we remove 1 from the s orbital, and we remove 3 from the d orbital. And so the electron configuration of chromium 4 plus is argon 3d2. And since you only have 2d electrons, it's going to be paramagnetic. Next we have cadmium 2 plus. Well, cadmium 2 plus is one of the trends that I said is diamagnetic, so we can just put this as diamagnetic because it's just going to have a completely filled d orbital. And lastly, we have hafnium 2 plus. So let's write the electron configuration of hafnium. So with hafnium 2 plus, we're going to remove from the s orbital first. So 2 electrons go, and then we have so since we have a partially filled d orbital, this would be paramagnetic. So again, this is how you determine if something has lone electrons or not. If it has lone electrons, it's going to have it's going to be paramagnetic. If it has only paired electrons, it's going to be diamagnetic.